You guys have been factoring a lot of different kinds of polynomials, but let's do one that's a little bit familiar. When we say quadratic polynomials, we've kind of talked about quadratics already, but what we mean is three-term polynomials. So anytime we have three terms, we're talking, usually talking quadratic, and we'll have some variations on that. So let's just get to an example that has a little bit of a kink in it. So when our leading term is negative, I have negative x squared plus 10x plus 75. My advice here is that when the leading term is negative, we factor that negative out as a greatest common factor. So advice would be to factor negative out of leading term. And how that's going to look in our next step is we have a negative. To undistribute the negative, we get x squared minus 10x minus 75. And now we're just kind of down to a leading coefficient of 1, and this is a very, very familiar kind of polynomial that we factor. So when we factor trinomials, we pull them into two binomials, and you do ask yourself, what's the simplest possible thing that multiplies to become my leading term? That would be x and x. I know that I have a negative 75, so what has to follow is opposite sign. I need a positive and a negative. And I essentially need two numbers to multiply to 75 and add to 10. Now, other advice I have here is to play with the numbers. This is something I learned, some words I learned from Mrs. Manton, but when you play with the numbers, you get a better sense in the long term of which numbers multiply and add to which sets. The more you kind of succumb to tricks and little things that you kind of do to sort of get to the result without a lot of thinking, the harder that some of the later examples are. So don't do that. Just think of what the numbers that multiply to 75. I know that 3 and 25 multiply to 75, but those are nowhere near 10 apart. I don't want to do something like 1 and 75. I know 75 is divisible by 5, and if I do the work to put 5 into 75, you get 15. Those are 10 apart from each other, so if I make it a negative 15 and a positive 5, that will multiply to become what I need. And this is a fully fine factored form. You're going to see your answer keys look a little bit more like this, where they do a 5 plus x times a 15 minus x. Can you tell me why these two things are the same thing? Well, in the end, I know you want to know which one I prefer, and I would prefer this one. It may differ a little bit from your answer keys, but there's a reason that we tend to like the ones with the positive leading coefficients, and that's coming a little later, not too far from now. Okay, let's do another one. 3 minus a 2z minus a z squared. Okay, again, this is a polynomial. You may be tempted to go right away to the factoring step, but I'm going to pull the negative out and make this a positive z squared plus a 2z minus a 3. And then it's just a simple matter of what numbers multiply to negative 3 but add to positive 2. That can only be plus 3 and minus 1. So I want to show you what that looks like if I actually have this as a 3 minus a 2z squared minus z to the 4th. And I want you to compare that with what we just did right up above, because it's very, very similar. Up above, anyway, this could be modeled as a quadratic. If I can say let u equal z squared, and that means u squared is z to the 4th, then this just becomes 3 minus 2u minus u squared. Now, you don't really have to write it like that, and I'll show you why. I just want you to see that if we pull the negative and made this a negative z to the 4th minus 2z squared minus 3, sorry, that would be plus 2z to the 4th minus 3. I don't actually have to do any of this here, because I can just treat this like we did up above. I just know that to multiply to get to z to the 4th, it's going to be z squared. This is going to be z squared, and I still have that same plus 3 minus 1. The difference now is that I can take this one step further with the z squared minus 1. And we're going to do this a lot on you guys where we have factoring that goes to more factoring. So z squared plus 3, and then this z squared minus 1 is a difference of two squares that factors into z minus 1 and z plus 1. So this would be the fully factored form. Okay, next one. Let's see what number we're on, number 4. Let's do one that has a leading coefficient that's different than a 1. Okay, so we're going to do a 6t squared plus 4t minus 2. Well, the thing with this is that we always want to take out a greatest common factor whenever we can. In the previous 3 problems, that greatest common factor was a -1. But in this problem, it's just a 2. So I'm going to pull a 2 out and get a 3t squared plus 2t minus 1. If I then pull that apart, I just want to try to make this about as easy as I can. I know I have to multiply a 3t times a t to get to a 3t squared, and I know I have to multiply a 1 times a 1 to get to a 1. So now I'm just going to play with the signs in the middle. If I go outer, that's going to be a positive 3t, the way it is now. I want it to be a plus 2. So let's try a plus there and a minus here. Then I get plus 3t and then minus 1t to get to the positive 2t in the middle. So this works. This is a fully factored form. I'm going to put a little note on the side, greatest common factor first. Okay, continuing on, let's do 20 over x squared plus 23 over x minus 21. And I want to factor this. Well, this should trigger a memory back when we did divided by x's, when we did systems of equations. Remember, we'd have like 1 over x plus 2 over y is equal to 1/4, and you would let u equal 1 over x. We're going to do the same thing here. I'm going to let u equal 1 over x and do a substitution. By the way, if u is equal to 1 over x, u squared is equal to 1 over x squared. And 20 over x squared is the same as 20 times 1 over x squared. This would be plus 23 times 1 over x, and then minus 21. So what I'm going to do here is just kind of replace or substitute and give me a 20u squared plus a 23u minus a 21. Now I have something that I can try to factor. There's no guarantee that everything's going to factor, but we're going to want to play around with this a little bit. So I know that 20 is going to split up into 2 and 10, 1 and 20, or 4 and 5. Those are my options. I typically will start with the middle one, so I'll try a 4 and a 5 with a u and a u. And then 21 could be 21 and 1. Well, if it was 21 and 1, 21 times 4 and 21 times 5, those are too big. We're not going to get to 23 with that. So I want to try a 3 and a 7. So let's try 3 and 7. So if I do 7 times 4 is 28. 5 times 3 is 15. That's not going to get me to 23. So let's try swapping the 7 and a 3. Let's try this, 35 and 12. Okay, so if I do a plus 35 and minus a 12, that's going to get me to positive 23. So that's the factored form with the u's, but remember, u is equal to 1 over x. So the real factored form is 4 over x plus 7 times 5 over x minus 3. Okay. Sometimes we get these ones that are looking a little bit familiar but not quite. So let's try this, where I have an 18t plus 1 squared minus a 51t plus 1 minus 100. This is going to be challenging for a few reasons. First of all, if you step back and kind of blur your eyes a little bit, you may see that I have something squared as the leading term minus another constant times that something and then minus a constant. So I could do another let here. I could let u equal t plus 1. That way, what I really have is an 18u squared minus a 51u minus 100. Okay. Let's look for a greatest common factor. Really, 100 is 10 squared, and that's made up of only 2's and 5's. And 18 has 2's, but 51 doesn't have 2's or 5's. So there's really nothing I can take out as a greatest common factor. So this is going to be about as challenging as they come. We're going to want to separate this out. And I know that 18 is made up of 2 and 9, 6 and 3, or 18 and 1. I always tend to try the numbers that are more centralized first, or closer together, so 6 and 3. 100, you could try 10 and 10, but here's the thing. If I put 10 on the left side, that's paired with a 6, that means I could have taken a 2 out, because I could factor a 2 out of 6u and 10. So it can't be 10 and 10, because if it was, I would have been able to take a 2 out of the original polynomial, and I can't. That's kind of a tip I have with factoring, that if you make a factor that has a greatest common factor that's not present in the original trinomial, then that's not the right one. So 100 can't be 10 and 10. Let's try 25 and 4. Okay, again, if I put the 4 with the 6, I could have factored a 2 out, but I can't in the original, so let's try the 25 with the 6 and the 4 here. Just see what happens and if we get anywhere close. 25 times 3 is 75. Then 24, 75 plus 24 won't work, but 75 minus 24 is 51. So if we make this a negative 75 and a positive 24, boom, we get it. My only task now is to put the t plus 1 back in. So 6u is actually 6t plus 1 minus 25, and 3u is actually 3t plus 1 plus 4. If I distribute, I get a 6t plus 6 minus 25 is minus 19, and then I get a 3t plus 3 plus 4 is plus 7. And I just need to check that the 6t minus 19 and the 3t minus 7 can't factor. They can't. 19 and 7 are both prime. So box that in, and that's our final. It's helpful now just to review the factoring types that we've talked about. So we have two-term factoring, which comes down to two types that we've seen. We've seen the difference of two squares, so something like u squared minus v squared. We've seen a difference of two cubes, which could something like a cubed plus or minus b cubed. And those have different factoring patterns. I know that this first one is u minus v times u plus v. I know this second one splits up into a binomial and a trinomial. The binomial is going to have the same sign as the original two-term difference of sum of cubes, and the trinomial is going to have a squared, b squared, ab in the middle, same, opposite, and always positive. Remember, this notation here means opposite of whatever this was. Same, opposite, and always positive. Then we have three-term polynomials, which we just did. That's everything up here. So that's everything like the ax squared plus bx plus c, things that look like that. Then we have four-term polynomials, and we've done two major types of that. We've done the 1 and 3, or the 3 and 1. 1 and 3 or the 3 and 1. That looks something like this, where I'm able to take like an ax squared plus bx, oh sorry, let me erase that and just kind of get something. Let's do x squared plus 2xy plus y squared minus z squared. This is an example of a 3 and 1, where I factor the first one as x plus y squared minus z squared, and then I factor the 2 as a difference of squares, x plus y minus z and x plus y plus z. The 1 and 3, let me kind of move this with the 3 and 1. The 1 and 3 reverses that, where it's z squared minus xy minus 2xy minus y squared. And it just takes a little bit of experience to try to recognize that I can pull out a negative and make this x squared plus 2xy plus y squared, and then get z squared minus x plus y squared. Factor that as a difference of squares, z minus x plus y and z plus x plus y. And then finally simplify that, z minus x minus y and z plus x plus y. The last type that we've had were the 2 and 2. And the 2 and 2 typically come from multiplying two binomials together that may not have a lot in common. So if I just do this, and I get ax plus bx plus ay plus by, and I shuffle those around and try to make something that might try to fool you, this is in a different order. But I can look and see that these two clearly have something in common. And if I pull an a out, I get an x plus y. If I pull a b out, I get an x plus y. So if I factor the x plus y out, I'm left with an a plus b. So this is a light review. Remember, there are multiple videos on our class calendar with each of these different types and many examples of the different types. So that's it. Check calendar and the board for homework, and I will see you guys later.